This silhouette is unmistakable on the horizon, a vast flat deck lined with the predatory profiles of fighter jets, the angular shapes of the superstructure, a wake of churning water stretching for miles behind the stern. This image is presented to us as the ultimate triumph of engineering.
A symbol of unchallenged hegemony, capable of redrawing the geopolitical map of any region with a snap of the fingers.
It seems that this steel mountain is as invulnerable as the very idea of global domination. But this majestic image is merely an optical illusion. If you step away from the press cameras and approach the edge of the runway, you will feel not triumph, but a continuous, exhausting vibration. You'll smell the scent of burnt jet fuel, acrid sweat, and salt ingrained in the metal. Behind this facade of total control lies a history of an endless struggle for buoyancy, a history of catastrophic fires, snapped cables, radiation alerts, and logistical despair. Catapult rails tear out the landing gear struts. Steam pressure ruptures pipelines. Thousands of kilometers of cables slowly rot in the corrosive, salty brine. The supply chains on which this colossus's life depends are stretched to the limit and ready to snap at the slightest glitch. This is not just a warship. It is an artificially sustained, extremely unstable sovereign territory.
A massive floating factory for the production of kinetic violence.
By the end of this dive, it will become clear why the most expensive military machine in human history is also the most fragile, and why a $13 billion instrument requires an entire fleet just to survive in open water. But to understand the nature of this vulnerability, we must go back to the beginning, to a time when the ocean was simply an absolute, indifferent void, and the idea of controlling it seemed madness. The ocean physically abhors right angles and flat surfaces. Water demands that shipbuilders create streamlined shapes, sharp bows, and a low center of gravity. A storm wave breaks everything that resists its kinetic energy. Aviation, on the other hand, demanded a perfectly flat surface. An airplane needed a stable, level surface for takeoff and landing. These two physical requirements were completely incompatible. Combining them meant defying the fundamental laws of material resistance. The first experiments were an act of sheer desperation. Wooden platforms were laid on the bows of cruisers. Pilots accelerated fragile structures made of calico and slats, trying to take off from the shortboard before the ship's bow plunged into the wave. It was a one-way ticket.
Landing back on this moving, bouncing target was practically impossible.
For the system to work, the platform had to be gigantic. In 1920, the US military took the unwieldy coal-carrying ship Jupiter and stripped it of all its superstructures. On top of the deep, bulbous hull, they erected a long wooden platform on tall steel supports. The ship was named the Langley. It looked ridiculous, lopsided and heavy. Coal dust was still seeping into the bulkheads when the first biplanes began landing on its deck. The main internal limitation became apparent immediately.
Raising the runway to a height of several dozen meters meant raising the center of gravity to a critical level. The ship began to behave unpredictably in the water.
It rocked with every shift in the wind. Every maneuver threatened to capsize it. To maintain stability, engineers were forced to abandon heavy armor. The deck remained wooden and the sides thin. Thus was laid the genetic defect that would determine the fate of these ships for decades to come. The aircraft carrier was born as a glass cannon, a weapon of colossal, striking power, yet lacking the basic ability to withstand a blow. In the 1930s, the concept began to take shape. American admirals recognized the enormous potential of naval strike aviation. True steel giants of the Lexington and Yorktown classes were launched. These were no longer the slow, converted coal carriers of the era of the first tentative experiments. They were built on the long, sleek hulls of unfinished battlecruisers. Naval treaties of the time forced designers to seek new, unconventional solutions for the fleet. They developed a speed of 30 knots, which was incredible for their size. Powerful turbines allowed these enormous floating airfields to keep pace with destroyers. They cut beautifully through the ocean waves, leaving a wide white trail of foam in their wake. Each of these giants proudly carried dozens of modern combat aircraft on board.
At ceremonial parades and large-scale exercises, they looked like absolute predators of the sea.
Their outward appearance exuded monumental strength and invincible American power. But beneath the pristine wooden deck lay the anatomy of a future disaster. The battleship's heavy artillery had given way to vast empty spaces for aircraft. The aircraft carrier was by no means a classic warship with thick armor plating along its sides. It was essentially a giant floating gas station combined with a massive explosives warehouse. The designers sacrificed reliable protection for the sake of speed and maximum aircraft capacity. The internal layout of these ships harbored a constant deadly threat to the crew. The massive, fuel-hungry air group required astronomical quantities of high-quality fuel. The aircraft could not fly on heavy and relatively safe naval fuel oil.
Deep within the ship were giant tanks containing hundreds of thousands of gallons of high-octane aviation gasoline.
These tanks were hidden as deep as possible, directly above the double bottom of the steel hull. Such volatile fuel evaporated rapidly, even at the slightest fluctuation in outside temperatures. Flammable vapors constantly accumulated in the ship's enclosed lower compartments. Dealing with gasoline vapors became a daily routine for all deck mechanics. Powerful fans ran around the clock to ensure mandatory ventilation of all hazardous holds. Kilometers of completely unarmored thin pipelines stretched upward from the deep tanks. They led directly to the open flight deck and enclosed hangars housing equipment. Highly flammable death constantly flowed through these vulnerable veins. The slightest damage to a pipe threatened an instant spill of a massive amount of fuel. The proximity of fuel and ammunition made the situation even more critical. In those same narrow, dimly lit corridors, sailors moved heavy weapons every day. People manually rolled bulky torpedoes and hundreds of heavy aerial bombs. Any accidental spark from static electricity could trigger a devastating chain reaction. The ban on smoking in the hangars was enforced with incredibly strict discipline. Between certain death and the crew stood only a thin steel bulkhead and the strictest fire safety regulations. For many years, this fragile system functioned only thanks to ideal peacetime conditions. Aircraft carriers had never once been tested under real enemy fire. The U.S. Navy firmly believed in its new expensive mechanical toys. Admirals stubbornly ignored the fact that the internal design defied the logic of survival in combat. Exercises demonstrated only offensive power, hiding fatal design flaws from public view. The ships were built for ideal conditions for delivering the first strike. World War II shattered the illusion in a matter of months. Harsh reality quickly stripped the American steel giants of their glossy sheen. The brutal Pacific Ocean became a vast, merciless laboratory for testing the durability of the technology. It was here that the breaking point of these complex systems was tested by a powerful kinetic impact. Experienced Japanese pilots quickly identified the American fleet's main vulnerability. They realized that a massive aircraft carrier was far weaker than a standard heavy cruiser when hit directly. The difference in armor became a decisive factor in the first major naval battles. When a heavy aerial bomb pierced the thick armor of a battleship, it left only a jagged hole.
This temporarily disabled a single compartment, but the heavy ship retained its combat capability.
When a bomb pierced the thin wooden deck of an American aircraft carrier, the consequences were catastrophic. The deadly charge struck directly into a closed hangar full of fueled aircraft. The explosion occurred right in the center of a massive storage area filled with suspended torpedoes and spilled fuel. The famous Battle of the Coral Sea clearly demonstrated the true cost of engineering compromises. The massive aircraft carrier Lexington sustained heavy torpedo and bomb hits from the Japanese Air Force. Through incredible efforts, the heroic crew temporarily brought the raging open flames on the decks under control. The massive ship stubbornly maintained an even keel and even continued to successfully land returning aircraft. The captain and officers on the bridge were absolutely certain that the mortal danger had completely passed. But the real enemy was lurking deep within the bowels of the damaged steel Leviathan. The hidden damage turned out to be far more dangerous than direct hits from enemy bombs. The violent shaking inside the hull caused the fragile welds on numerous fuel lines to rupture. Deadly high-octane vapors began to fill the enclosed lower compartments rapidly and completely silently. Exhausted crew members, caught up in the chaos of battle, simply failed to notice the dangerous concentration of invisible gas in the air. All it took was a single tiny spark from a ship's generator that had been accidentally turned on. That spark became a fatal blow to the pride of the U.S. Navy. A monstrous internal explosion literally tore the huge ship to pieces from the inside. The massive flight deck swelled up terrifyingly and cracked along its entire length. Heavy armored doors flew out of their steel hinges, mercilessly crushing people in their path. The fire instantly engulfed all decks, permanently cutting off escape routes for hundreds of sailors. This magnificent modern ship was not actually sunk by Japanese pilots. It destroyed itself due to its inherently flawed design. It was a true physiological overload of the entire safety system of the massive vessel. The built-in fire suppression systems simply could not cope with such a colossal volume of flames. The temperature of the fires in enclosed spaces quickly reached absolutely incredible levels. The heat was so intense that thick aluminum internal bulkheads melted easily. People burned alive in hermetically sealed, scorching compartments without a single chance of rescue. Survivors suffocated painfully from the thick toxic smoke of the ship's wiring burning profusely. Under these most extreme conditions, the fleet saved its precious ships not because of their original design.
Survival was ensured solely in spite of all the engineering flaws built into the ships back at the shipyard.
Thousands of ordinary sailors used their own bodies to block the path of the raging fire. With heavy fire hoses in their scorched hands, they stubbornly halted the spread of the infernal flames. Men worked for hours in pitch black, acrid smoke, standing knee-deep in churning, boiling water. Human resources were used as insulation to compensate for structural fragility. After the war, jet aircraft arrived on the decks. They were 3 times heavier than piston engine planes. They approached for landing at terrifying speeds, and for takeoff they required a runway that simply did not exist on the ship. The old flat deck turned into a death trap. If a jet pilot missed the arresting wire, he would crash at full speed into the aircraft parking area at the ship's bow. The cost of a single pilot error had become too high. It threatened to destroy half the air group. The system needed a radical overhaul. Salvation came from Britain in the form of 2 brutal but ingenious mechanical solutions. The first was the angled deck. The landing strip was angled away from the ship's longitudinal axis. Now, if a pilot failed to catch the cable, he faced not a wall of other planes, but open sky. He could go full throttle and make a go-around. The second solution was the steam catapult. To accelerate a 20-ton hunk of metal to takeoff speed over a 90-meter stretch required primal force. Engineers tapped into the ship's own boilers, drawing off steam at critical pressure. This steam accumulated in huge receivers below deck and was then released into the catapult cylinders with the force of a sledgehammer. The shuttle propelled the aircraft forward with an acceleration of several Gs. The stop was no less brutal. Engaging the brake cable is like a controlled car crash. A steel cable as thick as a hand catches the hook and pulls the hydraulic pistons located below deck, absorbing colossal kinetic energy. The aircraft carrier survived and adapted, but the price of this survival was physical. The deck became a zone of extreme mechanical stress. The pipes hidden beneath it groaned under the pressure of steam. The vibration from every launch loosened the welds. The ship ceased to be merely an airfield. It became a giant pneumatic gun, constantly firing out aircraft. The noise level on the upper deck exceeded the pain threshold. Without heavy hearing protection, eardrums would burst in seconds. The new form demanded that both metal and men operate at the absolute limit of their endurance. The next crisis was logistical. The enormous aircraft carrier required a colossal amount of energy just to move across the ocean. Accelerating at full power against the wind to launch heavy interceptors, it guzzled thousands of tons of fuel oil. The ship was tethered to slow, unwieldy tankers by an invisible but rigid umbilical cord. It had to regularly slow down and break formation to refuel. As it cast off the cables and took on fuel, this giant became an incredibly easy target for enemy submarines for hours on end. The search for an alternative led engineers to a completely new, revolutionary technology. The solution seemed like an absolute triumph of cutting-edge human physics and engineering. In 1961, the Enterprise, the world's first true nuclear-powered aircraft carrier, was ceremoniously commissioned. The designers took an unprecedented and incredibly bold step in naval shipbuilding. 8 powerful nuclear reactors permanently replaced the familiar dirty oil-fired boilers. The era of smoking funnels and constant fuel shortages for massive propulsion engines had come to an end. The promise made by military theorists sounded like a fantastic breakthrough in strategy. The ship gained a previously unattainable, absolutely endless range. It could easily circumnavigate the entire globe at maximum speed without slowing down for a single second. The commander of such a vessel gained absolute tactical freedom of maneuver anywhere on the planet. There was no longer any need to frantically calculate the remaining heavy fuel supply to the nearest friendly base. It seemed that the age-old problem of massive size and complex logistics had been solved by the military once and for all. But every ingenious technical solution inevitably comes at a new, high price. By replacing conventional fuel oil with enriched uranium, the fleet did not merely change the type of fuel used, it effectively integrated a fully fledged and highly dangerous nuclear power plant into the warship itself. Such a coexistence required entirely different safety standards and the highest quality control and construction. From that historic moment on, the very heart of the massive ship became a strictly restricted, secret zone. Only specially trained and thoroughly vetted personnel had access to it. Moreover, during its long service, an utterly insoluble paradox of infinity unexpectedly arose. The nuclear reactors themselves could operate continuously for decades without replacing the uranium rods. But the fighter jets on deck still flew on conventional, expensive aviation kerosene. And the numerous pilots and deckhands still needed fresh food and clean drinking water every day. The aircraft carrier could sail forever, powerfully cutting through the waves with its giant bronze propellers. But its formidable air wing quickly went blind and stalled without a constant supply of new, fragile spare parts and heavy bombs. The ingenious nuclear engine never severed the old logistical umbilical cord. It merely made it seem more absurd against the backdrop of high-tech triumph. The massive nuclear-powered vessel unexpectedly found itself hostage to the most ordinary human and simple technical needs. The ruthless reality quickly cooled the fervor of theorists of fully autonomous warfare. The naval forces were forced to build even more high-speed supply ships for their new insatiable flagships. The ship with the perpetual motion engine still waited obediently once a week for the supply transport to receive pallets of frozen chicken and thousands of gallons of JP-5 for its fighters. By the era of the Nimitz class, aircraft carriers had reached a displacement of 100,000 tons. Engineering ingenuity had transcended the boundaries of conventional naval shipbuilding and created veritable steel leviathans. The height of these staggering giants, from the deep keel to the top of the mast, exceeded that of a 20-story residential building. They had grown to such colossal proportions that the human mind could no longer adequately perceive them as a single floating object. It took a good half hour of very brisk walking to go from one end of the enormous ship to the other. Sailors could serve on the same ship for years without ever accidentally encountering one another. The hull of the enormous ship had quickly transformed into a self-contained, multi-level metropolis without a single window to the outside. Toxic coolants, fresh water, and volatile fuels circulated continuously under immense pressure through its tangled steel veins. Thousands of kilometers of thick cables entwined every compartment like the complex nervous system of a colossal living organism. The internal environment had become completely and irrevocably artificial. Fresh sea air was carefully filtered and forced with a loud roar through a tangled labyrinth of narrow ventilation shafts. After passing through long, dirty metal pipes, it inevitably acquired a persistent, unpleasant taste of iron and used engine oil. The acrid chemical smell of aggressive aviation fuel seeped imperceptibly through the tiniest micro-cracks in the steel bulkheads. It permanently permeated everyday clothing, thin government-issued sheets, and even the very skin of every crew member. It was absolutely impossible to wash away this clinging, distinctive scent of deck aviation with even the strongest soap. The layout of this floating, enclosed city was utterly unforgiving to its permanent residents. Precious space was saved with extreme rigor, cramming people into cramped quarters utterly unsuitable for normal rest. Directly beneath the thick, armored flight deck lay multi-tiered, stuffy sleeping quarters for junior mechanics and sailors. This endless ocean voyage was a veritable conveyor belt of sensory deprivation for the entire crew of many thousands. The complete deprivation of natural warm sunlight quickly and mercilessly disrupted all the natural circadian rhythms of a healthy person. The hard metal deck beneath their feet vibrated slightly but distinctly around the clock from the ceaseless operation of the giant propellers. Stress built up relentlessly in the sailors' young bodies, just as surely as fatigue accumulated in the old load-bearing frames. Constant nervous strain and hard labor often led to breakdowns among the exhausted crew. The ship mercilessly drained the life force from its people in order to constantly maintain the flying machine's perfect combat readiness. Parallel to the severe internal living conditions, the Leviathan's external strategic vulnerability grew rapidly. The giant, weighing 100,000 tons of steel, with a nuclear reactor and thousands of lives on board, had become too valuable a military asset. No sane admiral could afford to recklessly risk such an incredibly expensive treasure in actual close combat anymore. The loss of even a single such unique vessel to a cheap missile strike would mean a true national geopolitical catastrophe. Therefore, the proud and incredibly powerful aircraft carrier was forever deprived of the right to operate carefree in the world's oceans in proud solitude. It became vitally necessary for it to have dense, constant, and very expensive multi-layered protection against any unexpected external threats. Its devastating long-range projection of power became forever inextricably linked to its own extreme slowness and visibility on radar. Modern hypersonic anti-ship systems made the appearance of such a colossus within the enemy's strike radius an unacceptable, fatal mistake. It required billions of dollars in protection simply to reach its launch position. By the beginning of the 21st century, the old analog systems had reached their physical limits. The Nimitz class could no longer generate enough electricity for the new radars. There was simply no physical space left in its cable shafts to lay fiber optic cables. The ships began to suffocate under their own weight and technological obsolescence. The response was an attempt at radical surgery, the Gerald R. Ford class. The cost per unit exceeded $13 billion. Engineers decided to discard everything that had worked for decades. Steam catapults, whose mechanics were crude but straightforward, were replaced with electromagnetic ones, EMALS. Hydraulic bomb lifts were replaced with programmable electric motors. They attempted to digitize the ship, turning the giant warship into a floating server. But the reality of the ocean does not forgive overcomplication. Sea salt, humidity, and high-voltage electromagnetic fields came into conflict with the delicate electronics. The new catapults began to malfunction. Software glitches prevented the system from correctly calculating the thrust needed to launch aircraft of varying weights. The state-of-the-art weapon elevators refused to lift bombs from the magazines due to issues with the program code, leaving the air wing without ammunition. A machine costing as much as the budget of a small country was paralyzed by bugs. Instead of repairing pistons with a sledgehammer and a wrench, technicians were forced to wait for a firmware update. Digitization did not simplify the system. It created invisible layers of vulnerability. The ship's computer network became its central nervous system, and any failure in it led to paralysis of the machinery. The aircraft carrier had become too smart to operate reliably under conditions of severe physical stress. At the same time, a silent war raged against the oldest threat of all, corrosion. The ocean pays no attention to program code. It methodically eats away at steel. Millions of man-hours are spent every year simply scraping off rust, applying toxic primers, and painting bulkheads. If this process were to stop for even a month, the ship would literally begin to crumble beneath the crew's feet. Today, this $13 billion instrument of power has found itself in a geopolitical trap. It was created to project power onto the shore, to strike continental adversaries with impunity. But the geometry of war has changed. The enemy has learned to strike preemptively. Hypersonic anti-ship missiles and ballistic systems have emerged, specifically designed for a single purpose: to pierce the strike group's protective umbrella and strike the flat deck. The size of the aircraft carrier, which once guaranteed its unsinkability and power, has now become its curse. This steel mountain is impossible to hide. The ship leaves a gigantic heat signature from its nuclear reactors. Its radars emit electromagnetic waves visible from satellites in orbit. Its propellers create acoustic noise that submarines can hear from hundreds of miles away. The ocean has become transparent. The aircraft carrier glows on the enemy's monitors like a target at a shooting range. To survive in modern warfare, this floating airfield is forced to move farther and farther from the coast, to the very limits of its own aircraft's range. A weapon designed to strike terror along the coast now spends more and more time on evasive maneuvers and maintaining its own defenses. The power it projects now requires constant reaffirmation and colossal efforts to protect the weapon itself. Look at this silhouette once more. At this flat deck slicing through the ocean to the roar of turbines, you do not see a triumph of technology. You see the pinnacle of fragility. Over a century of evolution, the idea of a floating airfield has reached its physical, financial, and conceptual limits. This system survives not because it is robust, but because it is constantly, round the clock, being rescued. It is rescued by technicians scrubbing away rust. It is rescued by programmers patching radar glitches. It is rescued by destroyers taking on threats. Control over the ocean carries its own weight. And that weight is measured not only in tons of steel and megawatts of nuclear power, but also in the critical strain on human and material resources. Every dollar of those $13 billion is spent to delay the inevitable, the moment when water and metal fatigue take their toll. But as long as the reactors produce steam and the catapults can launch a plane into the sky, these steel islands will continue their course, leaving behind a trail of foam, vibration, and the illusion of complete control over the elements.